This next unit we'll be discussing is gases, the behavior gastics, and also calculations dealing with pressure. We like to start with gases as opposed to solids and liquids, primarily because, as odd as it seems, gases are easier to study. Despite the fact that it may be difficult to grasp onto a gas, we can't weigh a gas, etc., they're easier to study because they all behave the same. It doesn't matter really what gas we're looking at. Solids and liquids have a lot of other forces between the molecules that make them a little more difficult to study, and so we tend to reserve studying solids and liquids for the junior year. So let's take a look at some basic characteristics of gases first. Unlike solids and liquids, gases expand to fill their container. This is some information that we saw at the beginning of the year when we studied basic states of matter. Gases are also highly compressible. This means that we can take a gas and under enormous pressure compress it and change the container that they're fitting in. Gases also have very low densities. This is actually one of the reasons why gases are easy to study. Simply put, the gas molecules are far apart from each other, and because they're far apart from each other, they don't really interact with one another and they don't exert forces upon one another. This is one of the big reasons why gases are so predictable. We can't have a discussion about gases without talking about pressure. Pressure is a physics topic that we introduce here with chemistry because gases exert pressure and can also be affected by pressure. Pressure is simply the amount of force applied to a certain area. For example, the atmospheric pressure is the amount of weight per unit of area. We're at roughly 1 atmosphere because we're very close to sea level, and that is an entire column of air pushing upon you that extends all the way to space. Gases, we discuss pressure because not only do they exert it, but they're heavily influenced by it. Unfortunately, one of the minor hiccups that we encounter when we study gases is dealing with units of pressure. When gases and pressure were studied, it was done by a large number of scientists at almost the same time, and when they published their results, they often had their own unit that they used. And we'll start with the first official SI unit, a Pascal. A Pascal is 1 Newton, a unit of force, per meter squared, an area. Because a Pascal is so small, it is a very, very, very tiny unit, we commonly scale it up into a bar or a kilopascal, 1,000 pascals. Now, you may encounter the bar unit quite often in weather studies. Weather exerts a fair bit of pressure. 100 kilopascals is almost what we experience right here at around 1 atmosphere. You may also see older units, but still highly relevant units, millimeters of mercury or a torr. These are the same thing. In the United States, we don't use millimeters, we commonly use inches of mercury, and you'll often see our own atmospheric pressure measured in inches. The weathermen may say it's increasing or decreasing a certain amount, like so many inches. What they're referring to is a very, very old unit. It was derived from a thermometer, which was a closed glass tube with mercury inside. This is a little bit different than the thermometer. It was an open tube with mercury exposed to the atmosphere. The atmosphere would push down on the open tub, raising the mercury in the tube. How far it went up was quite literally measured, hence the term millimeters of mercury. 1 atmosphere, what you and I experience here, is equal to 760 torr, which is the exact same thing as 760 millimeters of mercury. Now, going from meteorology and weather studies, we also take a look at what's happening inside a laboratory environment. A manometer was commonly used early on with to measure the pressure of a reaction inside a closed chamber. Here we had a closed chamber. It was producing some kind of gas. Then we had a glass tube filled with mercury. Knowing the atmospheric pressure, and knowing the height change of the mercury, we could calculate what the pressure of the gas inside the tube was. Now, manometer is definitely an older unit, and we tend not to use it much because it involves mercury, a relatively dangerous metal, particularly the fumes. So these days, we tend to use electrical gas sensors, and in electrical gas sensors, there's a bladder. And since gases exert pressure and are also modified by pressure, as the pressure changes, the bladder may shrink or expand, and we send an electrical current across that bladder. As the bladder shrinks or expands, the voltage of the current changes, and this is how we measure pressure today in an electrical gas pressure sensor. So let's summarize what we know currently. Normal atmospheric is what you and I experience here. That's one atmosphere. Well, that is exactly the same thing as 760 torr, which is the same thing as 760 millimeters of mercury, and that is also equal to 101.3 kilopascals. And technically, kilopascal is the official SI unit. Despite that, you're still going to see atmospheres torr millimeters of mercury quite often because many scientists did work with gases and pressure at the same time and publish their own unit. This week, we're going to focus on our conversions of pressure because we do have to deal with quite a few units. Next week, we'll take a look at the gas laws themselves. I'm going to go ahead and introduce gas laws just because they're relatively simple to start with. Gas laws are going to involve volume, temperature, and pressure, and some variation of formulas. And we'll start with the first one, Boyle's law. In Boyle's law, this is comparing the volume to the pressure, and it is inversely proportional. What that means is that when volume happens to go up, because it's inversely proportional to pressure, the pressure must go down, and vice versa. If volume goes down, then the pressure must go up. Now, whenever we're looking at laws, if you see the term constant, any variable, here it's constant temperature, that means we don't need to worry about that in the formula. It doesn't change, so it's omitted from the formula. Another law is Charles' law, and this one is comparing the volume to the temperature. And here it's not inversely proportional, but directly proportional. And this means when volume goes up, the temperature also goes up, and vice versa. If volume happens to go down, the temperature also happens to go down. Notice here, because of the term constant pressure in the law, we don't include pressure in our formulas. Now, there are quite a few equations when we're studying gases. We're going to start with Boyle's law, and then we'll transition to Charles' law, Guy-Lussac's law, and finally the combined gas law. Taking a look at Boyle's law first. In Boyle's law, it's the relationship between pressure and volume. And you notice I have this written as P1V1 equals P2V2. The term 1, the subscript 1, merely means the starting conditions. So here, this is the starting pressure times the starting volume equals the ending pressure times the ending volume. Knowing three of these variables, any of these three, I can calculate what the other variable might be. In Charles' law, we have volume over temperature. Volume and temperature are directly related, and again, we have the initial volume over the initial temperature divided by V2 over T2, the ending volume and temperature. I also have Guy-Lussac's law. This is a relationship between pressure and temperature, and because it has a similar formula to Charles' law, this is also a direct relationship. When pressure goes up, temperature must go up as well. Pressure goes down, temperature must also go down. Finally, we'll end with the combined gas law, which is all three variables put together into one single formula. This was derived once Boyle's law, Charles' law, and Guy-Lussac's law were known. One important note that we will see later on. Because of the issue with Celsius and the fact that Celsius can be 0 degrees or even negative, that's a real value that can be measured and not unreasonable. 0 degrees Celsius, if you put 0 degrees Celsius in any of the laws that have temperature because the denominator, you end up with no answer. That's impossible. If you put negative Celsius, another real value that can be measured here on Earth, you end up with negative answers, like a negative volume or a negative pressure. That's physically impossible. For that reason, degrees Celsius cannot be used. Instead, we use the Kelvin scale. Now, the Kelvin scale we'll talk about. It's actually relatively easy to do. The degrees Kelvin is your degrees Celsius plus 273. We realistically can't reach 0 degrees Kelvin. That's something known as absolute zero. The molecules are not moving at that point. And we have to remember to be careful with our temperature. We'll remind you about that when we get to the temperature equations of Charles' law, Guy-Lussac's, and eventually the combined gas law. Once we cover the basics of this one, we'll enter what's known as the ideal gas equation, but that I'm going to save for another time. So this is the end of our first lecture. Today, we're going to focus on working on the equations that involve pressure conversions, so we have to deal with those first. And then we'll take a look at the individual laws and practice, how they work, how they look when they are actually involving equations, but also paying attention to the units. Let's take a look at a few example problems this week since we'll be looking at pressure conversions only. Remember, I still need to see all your work, and we're going to begin with our pressure conversions. 1 atmosphere equals 760 millimeters of mercury, which is the same thing as 760 torr. They're equal to the same thing. This is also equal to 101.3 kilopascals. All three of these units are equivalent to one another. This is our new conversion factor, similar to when we were looking at stoichiometry, and we'll be using these three, technically 4 units, constantly throughout our problems. This week, I'm only going to have you do odd. I'm not going to torture you that much. So odd only on your assignment. Make sure I see your work. I know it's going to be tedious, but this is actually pretty simple overall. It's a necessary step before we go into the gas laws themselves. Let's begin with number 1. 6.2 atmospheres converted into torr. I'll set up a dimensional analysis box. This should be familiar to us. And I think to myself, I need to cancel atmospheres and convert it into the unit that we're looking for, a torr. And this is where my conversion factors come in. 1 atmosphere is the same thing as 760 torr. 1 atmosphere to 760 torr. Now I can solve. Atmospheres gets canceled, and now we're left with torr. Plugging this into a calculator, 6.2 times 760 gives me 4,712 torr, my final unit. This is my final answer. A quick and easy conversion now that I have my conversion factors. So let's take a look over here. Most of these problems are relatively simple. I'm probably going to have you take a look at number 11 next here as a sample. Remember, we're only going to be working at odd first. So let's convert 526 millimeters of mercury into kilopascals. So number 11, 526 millimeters of mercury, converting into an unknown number of kilopascals. I'll set up a dimensional analysis box, so 526 millimeters of mercury. Box set up. I'm going to cancel millimeters of mercury. And then I'm going to go ahead and convert to kilopascals. Using my new conversion factors, I see that 760 millimeters of mercury is also equal to 101.3 kilopascals. Product of the top divided by product of the bottom, millimeters of mercury ends up getting canceled. So my end result is 526 times 101.3 divided by 760. Plug this into a calculator. 526 times 101.3 divided by 760 will get me around 70.11 kilopascals as my final answer. This will take care of 2 examples. The remainder of your work this week is relatively simple as long as you focus on your conversion factors. As a reminder, you only need to do odd, but please show me all your work. Next week, we'll focus on the gas laws themselves.